Okay, I'm going to talk about the power energy work that we have been doing in PPL for the last couple of years, and we don't really actually need to talk too much about why do we need to do this work, but I still have some facts that I want to share. Data centers in the US consume about 2% of the total US energy budget. That's a figure from 2010, and they cost $5.1 billion and they consume energy equivalent to 77 billion kilowatt hours. And I just calculated the per annum energy consumption cost for 3 supercomputers based on a 7 cent per kilowatt hour figure, and they come out to be quite large. $4.5 million for Sequoia, Blue Water is 5 millions, and the K computer is close to 7.5 millions. These are my estimates based on the 7 cent value, and these are not the actuals that I've gotten from any of those facilities. What is more interesting is that 40 to 50% of this energy consumption goes to cooling costs. And although we have been hearing a lot about improving the PUE number for data centers, but the 2011 average for the PUE came out to be 1.8, which still shows that on average there is around 40%. The 40% of energy consumption still goes to cooling. And most data centers face this issue of hotspot, which is mainly responsible for a high cooling energy consumption number. According to some reports, 4% of the total cooling costs can be saved for every degree of machine room temperatures. In other words, if you decrease the machine room temperature by 1 degree Fahrenheit, you can save 4% of the total cooling cost. Not only that, you can save 50% of the total cooling cost if you run your data center at 80 degrees Fahrenheit instead of 68 degrees Fahrenheit. And these numbers are not, they don't suggest these numbers out of the blue. Okay, just do that. These are well within the recommendations given out by ASHRAE, which is the body that specializes in cooling buildings. So now we come to the crux of my talk, that why do we need thermal management? In the first part of the talk, I'll be talking about how high core temperatures can lead to high cooling cost. And the second part of my talk concentrates on the 10-degree rule for reliability, which basically says that for every 10 degrees Celsius increase in temperatures, the failure rate doubles. Okay. So in order to understand the behavior of core temperatures, we ran a 5-point stencil application for 10 minutes of time, and we plotted the average temperature for 128 cores that we were using, and that is shown in this solid line over here. And over here the dashed line shows the maximum difference that any core had from the average temperature. You can see that the average temperature starts from 32 degrees Celsius and goes up to 52 degrees Celsius. And what is more surprising and alarming is the fact that if you decrease the amount of cooling, or if you change the machine room temperature just from 23 degrees Celsius to 25 degrees Celsius, there is an increase of 6 degrees Celsius on average for the average temperature. And the more surprising or the alarming thing is that after you reduce the cooling, there is you can see a formation of a hotspot, which is depicted in this green line, that shows the maximum difference that any core had from the average temperature. And this value of 20 degrees Celsius basically says that there was a core that was operating 20 degrees above the average of the entire cluster. Dynamic voltage and frequency scaling is a technique which is very commonly used by researchers from non-HPC as well as HPC areas in order to reduce the power consumption. This we use this scheme we firstly use this scheme in a naive way, where we switch the voltage and frequency for any core that crossed a certain temperature threshold, and we did periodic temperature checks, and we scaled the frequency down for any core that crossed a certain temperature threshold. This is a processor timeline that shows an execution of using 16 cores for a 5-point stencil application. The green and the pink parts over here show the actual computation, whereas the white parts over here show the idle time. So what is basically going on in this execution is that in this first iteration, the top 4 cores heat up and they shift to a lower frequency. And since all of the 16 cores have the same amount of work to do, these top cores take more time to complete the same work that the bottom 12 cores are doing. And hence, since the application is tightly coupled, at the end of each iteration, the bottom 12 cores end up spending a significant time idling, waiting for the top 4 cores. Charm++ is very well suited to this problem. The migratable object concepts can be applied to the problem we saw in the last timeline, and the idea is that you can load balance the work between the hot and the cold cores to save some execution, to reduce the execution time and basically reduce the slowdown caused by DVFS. So based on that, we combined the temperature control with Charm++ migratable objects concept, and we came up with a load balancing scheme which we call as temperature aware load balancing, or temp LDB in the rest of the presentation. So the user can basically specify a temperature range and a sampling interval. The runtime periodically checks core temperatures after the sampling at each sampling interval, and it shifts the frequency down by 1 level if any of the cores has crossed that temperature threshold. And similarly, if any of the cores go below the lower range, it shifts the frequency up by 1 level. Once the temperature control has done scaling the frequencies, we end up in a load imbalance phase as we saw earlier. So at that time, we migrate tasks from the slower cores to the far faster cores in order to reduce in order to improve the load balance of the system. More details about the exact algorithm can be found in their paper Cool Load Balancer, which was published in IEEE Transactions on Computers. So in order to see the benefits of our scheme, we used a 128 core cluster on which we had total control, in the sense that we can apply DVFS on it, and we can also control the cooling of that room. We used actual power meters which were installed in the PDUs to get the machine energy consumption, and to get the cooling energy cooling energy power, we used an estimation and a model to estimate that, which was based on actual temperature reading, air temperature readings that we were getting for the cool air coming out of the air conditioner and the hot air being sucked into the air conditioner. We use 3 Charm++ applications as well as 2 MPI applications to see the effectiveness of our technique to constrain core temperatures. This plot shows the average core temperature once again on the y-axis, and execution time on the x-axis, and the two pink lines over here show the desirable range, which is from 47 degrees Celsius to 49 degrees Celsius, and you can see from the graph that our scheme was able to constrain the core temperatures for all the applications within that range. Not only that, in these runs, the core that had the highest temperature started 10 degrees Celsius above the average temperature, but at the end it ended up operating at 5 degrees Celsius above the average temperature. So we basically reduced that maximum difference from 20 degrees Celsius to 5 degrees Celsius. This figure shows the execution time penalty for all 5 applications for 4 different cooling levels. And the baseline for these runs is the run where we are not using any temperature control and all the cores are working at the maximum frequency. And the pink bars over here represent the execution time penalty, or the DVFS induced slowdown, using our load balancing scheme, whereas the blue bars show the naive DVFS scheme, in which we are constraining core temperatures, but we are not using any load balancing. So all the data points point towards a significant saving by using the load balancing scheme in combination with the temperature control. And it's interesting to see that as we as we go on decreasing the cooling or increasing the machine room temperature, the penalty generally increases for all the applications. But so does the benefit of our scheme in most of the cases. So just to understand what exactly is going on here, the earlier timeline that I showed had a few spots, a few holes of idle time. So this is once again a processor timeline for a run where we didn't use load balancing and a run where we did use load balancing. And you can see that these holes that are there in the no load balancing case are basically filled by tasks due to task migration in case where we are actually doing load balancing, and the difference in the timelines actually represents the reduction in execution time as compared to the scheme where we are not using the load balancing. In terms of machine energy consumption, our scheme was able to keep the energy consumption to the same level to the same level as the baseline case, which is to say that the machine energy consumption for constraining core temperatures and using load balancing was almost the same for most of the cases as the run where we are not using any temperature control and everything all the cores are working at the maximum frequency. This is mainly due to the high base power of the machine, coupled with the fact that due to DVFS, there is a slowdown and we are actually spending more time doing the computation. But still, if we compare our scheme with the naive version where we are not using load balancing, we still end up saving machine energy consumption in comparison to those runs. So we were using Intel X3430 single socket nodes. Which are pre-Nehalem. Yeah. I think they are probably 4 years or more older. So although we couldn't save a lot of machine energy consumption, we were able to reduce the cooling energy consumption by quite a bit. And once again, the light green curves show the temperature aware load balancing results, and the y-axis shows the savings in cooling energy consumption. So both the schemes end up saving a significant amount of cooling energy consumption, and our scheme saved a maximum of up to 57% of the total cooling consumption, and these numbers are once again based on the air temperature readings that we were getting. You can this work is published at SC as well as the IEEE Transactions on Computers journal paper, and for more details you can either contact me or look at those publications. So after seeing how can we constrain temperatures and what effect can it have on cooling energy consumption, we now look at how constraining core temperatures can improve the reliability of a machine. So this work is based on the fact that for every 10 degrees Celsius increase in temperature, the mean time to failure doubles, or in other words, for every 10 degrees Celsius increase in temperature, the failure rate doubles. Yeah, I was wrong the first time. The mean time to failure halves for every 10 degrees increase in the temperature, and we can model this relationship where MTBF is expressed as an exponential function of the temperatures. So in order to see what effect does temperatures make on the mean time to failure of a cluster, we ran a 5-point stencil application on the 128 cluster that we have access on, and we plotted a temperature histogram for that run. So each bar over here represents the number of cores that were operating at a certain temperature. The blue part over here shows the majority of the core, which I represent as the cool cores, whereas the orange part over here shows the hot spot in our cluster, which operates at almost 20 degrees above to what the cool cores operate. And based on this temperature data and the relation we mentioned earlier, we calculated the mean time to failure for each socket, and we basically combined those numbers to get the mean time to failure for the entire machine. And this red point over here shows the corresponding mean time to failure for this data, and it came out to be 5.5 days for our cluster, assuming certain constants for mean time to failure for each socket. So now we ask this question, that how would the mean time to failure change if we somehow remove this hotspot from here? In order to do that, we basically moved the hotspot back to the cool cores. And since we didn't have actual data for this, we did a simulation where we changed the mean of the hotspot back to 59 degrees, and we generated random numbers for temperature and used that in this relationship to come up with a mean time to failure for this new setting where we have removed the hotspot. And the mean time to failure in this case came out to be 7.5. After that, we considered that, okay, how would the mean time to failure change if we reduce the if we reduce the temperatures for the entire cluster, or in other words, if we shift the entire distribution towards the left. So for while moving from here to here, we randomly generated several temperature configurations, and we computed the mean time to failure for each of them using this equation, and the mean time to failure changed from 7.5 days to 12.5 days. And in order to verify all this, we ran our temperature aware load balancer for 2 different applications and different temperature thresholds, and we tried to see that whether it matched our simulations or not. So these points that you are seeing here, the J represents an application, Jacobi 2D, which is an application, a charm plus application. W represents Wave 2D, which is another charm plus application. This percentage over here shows the slowdown caused by DVFS due to temperature constraining, and this represents the maximum threshold selected for each experiment. So our experiments match pretty well with the simulation. And but the general trend is that if you want to increase the mean time to failure or reduce the failure rate, you will have to pay this execution time penalty or the slowdown which is caused by DVFS.
How do you measure the
So the mean time to failure is based on the 10-degree rule, which basically says that for every 10 degrees Celsius increase in core temperatures, the failure rate will double. Yeah. So for this experiment, we assumed that the mean time to failure for each socket is 5 years, and based on that, we came up with this. We came up with this equation. So basically, we are assuming that at 40 degrees Celsius, the mean time to failure is 5 years. At 50 degrees Celsius, it's the MTBF is 2.5, half of 5 years.
years to days?
So this is. So the 5 years mean time to failure is for each socket. Over here we are talking about all the cores. So the 128 cores. Yeah. So there is this other equation which we use to basically calculate the mean time to failure for n number of nodes, given that each node has a certain MTBF. It's basically the reciprocal of the failure rates of all the individual sockets.
Does that mean this is an extrapolation for much larger system? True or false?
Yes, yeah. This is an extrapolation, assuming a socket per socket MTBF of 5 years.
As extrapolation to a system with much larger number of nodes.
With 128 cores.
Okay.
So what we basically learned from all of this experiment was that by constraining core temperatures, we can basically select an MTBF. But this selection comes at the cost of a slowdown in the application. And the other important thing is that each application, since it has a different temperature profile, can basically result in a different mean time to failure for a cluster. So in other words, if you are running an application which heats the cores up very much, you should expect your machine to fail more frequently as compared to an application which doesn't heat the machines up very much. So now The execution time in an environment where we have faults can be represented by this equation over here, which includes the time to solution, which is a useful work, the time for checkpointing, the time to do recovery, and the time the machine takes to restart the computation. The important question we ask ourselves is that is the decrease in MTBF good enough to reduce the total execution time given the slowdown is associated in using DVFS? And we took the same equation and we incorporated the slowdown due to DVFS in this equation. So basically, if we reduce the temperature threshold, and in other words, we are saying that we are increasing the slowdown. So these red numbers over here, the mu, which represents the slowdown due to DVFS, will increase. But since we are constraining the core temperatures at a lower number, the mean time to failure will increase. So basically it all boils down to a trade-off between how much is the cost of the increase you are getting in the mean time to failure. In order to evaluate our model, we combined our temperature load balancer with fault tolerance and we used Charm++ to implement this strategy. And the migratable objects, as I was talking in the first part of my presentation, are a key over here, because due to migratable objects we reduce the execution time penalty due to DVFS very significantly. We improved our temperature load balancer by making it communication aware. So instead of randomly picking up tasks and migrating it to any underloaded processor, we migrate a task that communicates the most with an underloaded processor. The details of you can read more details about it shortly after we put our work on as a technical report. So in order to verify our model, we used the same cluster, but instead of having a 5-year MTBF per socket, we scaled down that number to 4 hours, because as I was showing earlier, with a mean time to failure of 5 years per socket, we have to wait around 5 to 6 days for one failure to come, which is clearly not possible. And I don't think the person who is responsible for that machine will actually allow me to test for real failures. So we scaled down that values to 4 hours, and we induced failures ourselves by killing processes. And we used three applications mentioned over here to test our hypothesis. So for each application, the baseline run is the one where we are not constraining core temperatures, and we induced errors based on M, which is calculated from the real data, the real temperature data that we get from doing those runs without any temperature constraints. And based on this M, we calculate a checkpointing period using Daly's formula. And for each of these applications, we do several temperature constrained runs for different thresholds. And for each temperature constrained run, we take M to be the maximum allowed temperature for that experiment. These figures show on the y-axis the reduction in execution time, and this is total execution time, which includes restart time, checkpointing time, and the useful work. And on the x-axis, we show different temperature thresholds to which we constrained the core temperatures. These small numbers, which are not very well visible over here, shows the times improvement in the mean time to failure for the cluster. For example, at 44 degrees Celsius, this number is 2.14x, which basically means that if you constrain this application at 44 degrees Celsius, you should expect the mean time failure to be 2.14 times what it was without constraining any core temperature. And we can see that for all three applications, we were able to reduce the execution time for up to 16%. And the interesting thing, which I don't have too much time to discuss, is that these applications, each of them have a different optimum temperature threshold, and they end up having different reductions in execution time. And this is something which is more discussed in the paper that we are going to submit to supercomputing. And Each of these data points represents experiments which were more than 1 hour and which had more than 40 faults in each of them. And the dashed line over here shows the predictions of the model that we showed earlier, whereas the solid lines show the actual experimental data. And from these figures, we can conclude that our model did a pretty good job in predicting the effects, the reduction in execution time.
Again, 1 hour experiment, 40 falls, something is wrong. So what's extrapolation?
So these, as the previous slide explained, that for the experiments we used a scaled down value for the mean time to failure. So instead of using 5 years, we use the mean time to failure of 4 hours per socket, which is very small, which is unrealistic. But if we,
So you mean that there are predicted 40 falls?
yes, there are predicted 40 falls.
The expectation of 40 falls sounds like there actually were 40 falls.
So these experiments are all induced faults. That's For our experiments, we were also able to save significant machine energy consumption, and these numbers are coming from actual readings that we got from the power meters installed on the PDUs for the machine. And we were able to save as much as 25% of the machine energy consumption. And we didn't, in this work we didn't actually do it, but if we incorporate the cooling energy savings that we could have gotten for this work, we might end up saving more than 40 to 50% of the total energy. But that's something we haven't done up till now. So after looking at the accuracy of our model, we tried to use the model and predict the benefits of our scheme for larger machines. And on the x-axis is the number of sockets, and in order to get this figure, we took real numbers which we got from by surveying literature. So for these plots, we used a mean time to failure per socket of 20 years and a checkpointing time of 240 seconds. So based on these constant, our scheme starts to give benefits after 50,000 sockets. And at the predicted exascale level of 200,000 sockets, our scheme can result in reducing 35% of the execution time. But before 50,000 sockets, it seems that we are incurring a penalty in basically an execution time slowdown of at most 9%. But if we really think about it, there is this penalty over there, but it's not basically for nothing. These numbers over here show the improvement that we got in the mean time to failure as compared to the no temperature constrained run. So for all the applications, we are basically improving the mean time to failure by at least 1.5 times to what it was without temperature constraints. So this penalty can if there is a high penalty of restarting a node, or basically if it costs a lot to replace a node, then reducing the mean time, increasing the mean time to failure might also benefit. And in a future work, we basically plan to evaluate the benefits of a temperature control for message login and parallel recovery for fault tolerance. And we are also planning to work on scheduling jobs for data centers under a fixed thermal and power budget. And in the very end, I'd like to share this picture which I got from yesterday, and despite all my efforts to improve its visibility, it hasn't improved. So this is a very interesting figure which shows the temperature readings that I got from Blue Waters yesterday. So although we have been hearing all this about that, after water cooling is here, we'll get rid of hotspots and all that, but looking at the readings that we got from Blue Waters yesterday, it didn't seem to be the case. So as we started moving from the first row towards the last row, and I don't think the rows number are actually correct because I might have skipped some rows, but in the first row, the temperature readings from what they told me, the temperatures were given for the cold water that is entering. So the cold water entering the first row was at 63, and there were two readings, 63 and 62, and I don't exactly know what these two readings represent. So in the first row, the cold water was at 63 degrees Fahrenheit, and as we move along to the back of the room, the last row had water coming in at 70 degrees Fahrenheit, which according to my small knowledge definitely points towards a hot spot. And this thing is only in one dimension. If we move across the row, if we move along the row, there might be some other differences as well. And I will like to acknowledge Professor Tariq Abdul for letting us use this precious cluster, without which I don't think I'll be able to conclude my thesis.
All right, thank you. Time for maybe one question. We are running late. Any question?
Perhaps one navigation could be useful. What we are doing with temperature is actually a restraint, not a constraint. Constraint is removing a degree of freedom from mathematical studies. Restraint is limiting the degree of variation of the degree of freedom. So it's if you want to, I guess it would be helpful if you could if you use restraint instead of constraint. That would be mathematically more correct. Constraint is mathematically when you completely remove the degree of freedom, so it doesn't exist anymore. Right, so if you apply the constraint, the temperature cannot move outside of the specified region. It has to be fixed. But with restraint, the temperature may fluctuate, and the stronger restraint, the smaller the fluctuation.
All right, thanks, Osman.